In 2012, NASA's probe Voyager-1 crossed the so-called heliopause, a giant bubble of electrically charged particles and magnetic fields surrounding the Sun. It was the first spacecraft to enter interstellar space. Voyager-1 and its twin Voyager-2 went into space in 1977, marking the beginning of an incredible space journey that would last forever. Currently, as of 2020, Voyager-1 is flying toward the unknown at a speed of about 38,000 miles per hour, being the fastest human-made object in space. Moreover, Voyager-1 is the most distant human-made object from Earth. Today, it is about 15 billion miles away from our planet. It would take nearly 24 hours for light to travel that distance. Since the beginning of its journey, Voyager-1 has flown past Jupiter and Saturn, passed through the Kuiper belt and the heliosphere boundary of the solar system, relentlessly transmitting valuable information to Earth. It is now in interstellar space, and despite all those unimaginable distances, in the future, it will encounter other star systems in its path. The first such star, which Voyager-1 will encounter after leaving its home solar system, will be AC plus 79 3888. It has no name, like Sirius or Alpha Centauri, but to put it simply, it's Gliese 445. Gliese 445 is located 17.6 light-years from Earth, in the constellation Giraffe. It's not in the constellation outline but within its boundaries. Its closest neighbor is the Polaris. Gliese 445 is a typical representative of red dwarfs. These stars make up the largest population in our galaxy, but they are too dim and small to be visible to the naked eye from Earth. Therefore, Gliese 445 is visible in our sky, but only when viewed through a telescope. This frugal glow helps keep the red dwarfs alive much longer than the Sun. It is believed that 20 of Earth's 30 neighboring stars are red dwarfs. The brightest representative and, at the same time, the closest star to the Sun is Proxima Centauri. Gliese 445 was formed just like other stars in the main sequence. First, the cloud of dust and gas was pulled together by gravity and began to rotate. After that, the material stuck together in the center, and at a critical temperature, it began to fuse. The mass of red dwarfs is up to 50% of the mass of the Sun. In our case, the mass of Gliese 445 is 0.14 solar masses. The reduced size of red dwarfs means that they burn at lower temperatures, reaching a maximum of 3,500 Kelvin. Gliese 445 has even lower temperatures. The low temperatures of red dwarfs mean that they are much, much dimmer than stars like the Sun, emitting very little light. In some cases 10,000 times less than our star. Because of their low temperature, stars of this type burn up their hydrogen supply very slowly. While more massive stars burn the hydrogen only in their core before coming to the end of their lives, red dwarfs consume all of their hydrogen inside and outside the core. This increases their lifespan to 1 trillion years. Scientists sometimes find it difficult to distinguish a red dwarf from another type of star, a brown dwarf. Brown dwarfs are cold and dull and are also often called failed stars because they never burn fusion at their cores. To find out whether a celestial object is a brown or a red dwarf, scientists measure the object's temperature. Brown dwarfs are even cooler and much more lightweight. Sometimes chemicals can give a clue, too. The presence of elements such as methane or ammonia, which can only survive at low temperatures, suggests that the object is a brown dwarf. The presence of lithium in the atmosphere also suggests that the object is a brown dwarf, not a red dwarf, which lacks this element. In addition, there are numerous red dwarfs with exoplanets surrounding them, although huge gas giants, like our Jupiter, are rare. Since these stars are dim, exoplanets are easier to find around them, so it makes them very popular with exoplanet hunters. The Kepler Space Telescope, which operated from 2009 to 2018, and TESS, which began operations in 2018, have examined many red dwarfs for possible Earth-like planets. But the main paradox is that scientists have long considered red dwarfs unsuitable for life. Their limited light and heat spoke to the fact that the habitable zone, the region where it is not too hot and not too cold and where water in liquid form can form, would be very close to the star. Which means that exoplanets would be exposed to its radiation, which is destructive to life. Other exoplanets may be in tidal lock with the star, that is, one side of it is constantly facing the red dwarf like the moon is facing the Earth. This means that one side would be too hot, while the other side would be too cold. Nevertheless, exoplanet systems in red dwarfs are considered on Earth to be potentially suitable for life. In 2016, such an exoplanet was discovered in the orbit of Proxima Centauri. And in 2019, astronomers announced that a second exoplanet may be orbiting far beyond the red dwarf's habitable zone. There are at least 7 Earth-sized exoplanets in the TRAPPIST-1 system, and many studies suggest that there could be life on at least some of them. By the way, long life is one of the reasons why red dwarfs are considered good sources of life on exoplanets, because they are stable for such a long time. As for exoplanets at our research object Gliese 445, so far they haven't been found, although this doesn't mean that they don't exist there at all. As we have already mentioned, tiny red dwarfs have a very long lifespan, but, like all other stars, they will eventually burn out their fuel supply. So what happens then? They will become white dwarfs, or the so-called dead stars. Exactly the same fate awaits our Sun. In short, the end of all red dwarfs is the same. To summarize, red dwarfs are the most common objects, at least in our Milky Way, and at the same time, the longest living stars. Now, we should mention the old saying, slow and steady wins the race. And it is to the representative of red dwarfs, the star Gliese 445, that our Voyager-1 rushes at full speed. The apparatus will reach this goal not soon, about 40,272 years. Voyager-1 will be moving and will pass within 1.7 light-years of this star. But the amazing thing is that all this time, Gliese 445 is also moving, and not just in outer space, but toward our solar system. In 40,000 years, this star will be just 3.45 light-years away from us. Nowadays, that distance is a little over 17.5 light-years. At the moment, Proxima Centauri is still the closest star to the Sun, but over time it will lose that position, giving it first to Alpha Centauri, then to the star Ross 248, and finally to Gliese 445. What is the future of our glorious Voyager-1? Next, after Gliese 445, it will have to leave the Oort cloud. It is estimated to happen in 56,000 years. And then pass by the stars GJ 686 and GJ 678 in 570,000 years. Admittedly, it will be just a dead piece of iron, albeit man-made, since all its equipment will be completely out of commission by 2025. What about Voyager 2, you may ask? After all, it is also moving, also flying into interstellar space, but in the other direction from its twin brother. In about 40,000 years, Voyager 2 will pass close to the star Ross 248. It is also a red dwarf, located in the constellation Andromeda, not to be confused with the galaxy of the same name. In about 296,000 years, it will pass within 4.3 light-years of the well-known star Sirius. Without a doubt, it is hard to say how the amazing journey of the Voyager brothers will end. Maybe they will wander the Milky Way forever, or maybe they will be destroyed by 1,000 micrometeorite impacts. Or it will be a single, but major collision. It may well be that the Voyagers will outlive the solar system, not to mention outlive those who created them. After all, if humanity will live to at least the year 40,272 is a big question.